Hi, I'm Michael Zaire from Team 4 of Embedded System Design in the fall of 2020, and I'm joined by my teammates Himoja Jinkala, Alan Mendoza, and Ethan Rockaway. Our goal for this project was to create a robot which can be used by the operator of an apple orchard to improve the orchard's efficiency by autonomously collecting fallen apples. A three-wheeled robot with various sensors mounted to it will scan its surroundings for anything that looks like an apple. It will then drive up to the first thing it sees and take a closer look. If the object looks like an apple, a robotic arm will grab it and place it in a collection basket mounted to the robot. Once the basket is full, an orchard worker will collect the harvest. Our robot must be able to detect apples from at least 20 feet away so that it can see all of the fallen apples within the broad branches of a tree. So that our system is economical for the orchard owner, it must also cost less than $400 in materials to make. Our robot must also be able to safely avoid humans and animals and be completely electrically powered in order to not interfere with the ecosystem. So here's what we came up with. The fully integrated robot has a LiDAR sensor which can see in all directions, a Pixie 2 AI camera used for determining if an object is actually an apple, and an ultrasonic sensor for getting an accurate distance measurement from the apple. Here we can see the robot functioning in a control environment. First, the LiDAR scanned the room for any targets. It saw 3 and started driving to the closest one. It then rotates so that the camera can look at the object and determine if it's an apple. Due to COVID-19 restrictions, we chose not to integrate the robotic arm, but at this step the arm would grab the apple and place it in the basket. The robot then drives to the next object that it saw. It does a full 360-degree rotation, but never sees a red object, so it moves on. Finally, it reaches the last object and rotates, then sees a positive target and stops. Next, I'll discuss the design and implementation of the rover component. The rover is the backbone of the system and must be reliable, robust, and simple to interface with. The rover only receives information from the navigation component. Navigation interprets all of the sensor data and tells the rover and arm how to move based on that information. Navigation broadcasts its state, which has several possible values. If in the navigating state, the rover will move at the direction indicated by the bearing field. Note the difference between a bearing and an angle. 0 is at a different location and the increment in reverse. Since the LiDAR gives its data in a bearing system, all of our data does the same. In navigation, if it is in the arrived state, it means that the rover is next to the target but not facing it, so we must rotate until the Pixie cam sees a red object. The rover will rotate until navigation state changes to idle, at which point it will stop and the arm will grab the object. If the state is anything other than navigating or arrived, the rover's motors will not move. The rover also outputs its state, either idle, moving, or rotating. This is not used by any other component, but is useful for debugging. Each motor's speed may be different at any given time, and they need to be accurate. A PID control loop accomplishes this. A PID loop works by considering multiple aspects of the measured input signal, modulating their strength using different coefficients, and using the result to develop an output control signal. The proportional factor is simply the error between the desired motor speed and the measured speed. The integral is a continuous sum of this error. Therefore, if the error is always positive or always negative, this factor will grow very large or very small, causing issues. Therefore, limiting the strength of this factor is important to the stability of the system. Finally, the derivative factor is simply the difference of the error from this time cycle and the error from last time cycle. A test program was developed to tune the coefficients for each factor. In order to reduce overshoot, which can cause significant inaccuracy of motion when driving, the system was tuned to be slightly underdamped. These are the coefficients that were settled upon. 0.1 is the largest Ki value that did not result in significant oscillation. KD is 0 because increasing it at all had no positive effect on the response for this particular system, meaning this is essentially a PI control system. With this tuning, the response looks similar to the one circled in red. When driving to a target, the rover drives at a bearing given by the LiDAR omnidirectionally. This means that the motors can be turning at any different speed, and the speed must be determined mathematically based on the given heading. The equation at the bottom is used to get the target speed for each motor. Each motor is assigned an angle. Since there are 3 motors in a triangle, these angles should be 120 degrees apart. They should also line up such that the cosine gives the correct value for a given heading. For example, say the requested heading is 0 degrees. Cosine of the 2 front motors with angles 150 and 30 will be at √3/2 of their max speed, and the rear motor at 270 degrees will be at 0 speed, which means the rover will be driving directly forward as desired. Rotation is simply achieved by turning all motors at their max speed in the same direction, such that the rotor rotates clockwise. The rover is highly reliable, but did not have the precision we expected. The validation plan document outlined several pre-programmed paths for the rover to follow, and its performance was judged based on how close it was to its starting point after it returned. Some of these tests are being shown now. The requirement for most of these test cases was to be within the robotic arm's reach of the desired location, which is about 15 centimeters. With longer paths, when using dead reckoning by controlling the rover simply based on time, the rover does not always meet this requirement. This will be remedied by constant input from the sensors and navigation, which would correct the path of the rover. The rover also has occasional jerks where the motor will briefly increase to max speed. Generally, this is short and infrequent enough to have little effect, though. The rover's runtime is only limited by its power. Extended tests were done running the rover in a circular motion for up to 30 minutes to see how far it drifts from the original position. The rover is robust to lost input data because it is not reliant on having constant input. While the performance of the system would be impacted if a message from navigation was missed, the rover would simply continue what it was doing previously until the error was corrected by navigation. The rover itself is not significantly limited by its operating environment, with the exception of challenging topology which would not likely be encountered in an apple orchard. The rover will be able to operate correctly as long as there are a Wi-Fi signal that it can connect to.
Our project used 3 different sensors to gain information about the rover's surroundings. The PIXI camera, seen here on the left, was used to identify color signatures in order to find our targets. Since the targets for our project was apples, the camera was configured to find the color signature for red objects. The PIXI camera communicates through SPI. It reads every 250 milliseconds, looking for blocks of the specified color signature. It then outputs to the MQTT server whether it sees a target or not. When a target is seen, information about the size of the target, such as the height and width of the block detected and the block's position in the PIXI field of view, is outputted. The second sensor, seen here in the middle, was the ultrasonic sensor. It communicated through a simple capture and timer. This sensor was used to capture horizontal distance and was configured to detect a range of 0 to 60 centimeters with a margin of error of plus or minus 1 centimeter. It measures the distance to the object in front of it and outputs this information to the MQTT server. The final sensor configured was the LiDAR sensor, seen here on the right. It communicates through UART. This sensor works as a 360-degree scanner with a range of up to 12 meters. It outputs many data points, each being a pair of distance in millimeters and angle in degrees. These 3 sensors work together to provide navigation with the data and information it needs regarding the surroundings of the triangular rover. Here is a video showing the configuration of the first sensor, the PIXI camera. In this video, you will see how the PIXI can be configured to identify a specific color signature. A bounding box is then drawn around the object that holds this color. As the object moves farther, closer, in and out of the frame, the bounding box follows. And this is the information the PIXI camera outputs to the MQTT server.
For the robotic arm, we use the Tinkerkit Brasio robot arm. The overall system is quite simple. We use an MQTT server to send and receive data. Then we use the board to generate 4 PWM signals, which will manipulate the 4 servo motors of the arm, which will then make the arm move. On the software side, we have 2 tasks, the robot arm command task and the robot arm task. The first task receives a message with an angle in degrees, a distance in millimeters, and then calculates the 4 servo angles that will make the arm grab the object at the specified angle and distance. Then it sends the message to the MQTT server. The second task is in charge of modifying the 4 PWM signals, which will make the arm physically move. So a full motion of the arm consists of grabbing the object, which is indicated by the first message, then dropping the item off at the basket, which is indicated by the second message, and then returning to the default position, which is indicated by the third message. It is worth noting that the servo angles for the first message will change depending on the angle and distance specified, while the servo angles for the second and third message will always be the same. This is because the basket is mounted to the rover, so we know where to position the arm in order to drop the item off, and our default position will always be the same. Once the arm returns to the default position, it generates a done message to notify the system that the arm is done moving. This will allow the system to move on to the next target. In order to test the reliability of the arm, first I had to find the range of the values for the angle and the distance. The angle depends on the pixicam, and the pixicam has an FOV of 60 degrees. This means that I have a range of plus or minus 30 degrees with respect to 90, because 90 is the starting position of the base of the arm. The distance is limited by the range of the arm, which I found to be from 10 centimeters to 17 centimeters from the start of the base. To test the reliability of the arm, I tested the angle in increments of 10 degrees in the range of 60 to 120 degrees, and I tested the distance in increments of 10 millimeters with the range of 100 to 170 millimeters. This gave me a total of 42 combinations. This allowed me to test every possible reachable angle and distance. I know my design is robust because it took around 20 minutes to test all 42 combinations. This was done with a Python script, but I had to manually move the object. This also tells me that the arm can stay connected, send and receive data to the MQTT server for at least 20 minutes. I didn't want to go any longer than 20 minutes because I was afraid I would burn or damage the servo motors on the arm. For this project, we had some restrictions. The first one was that the arm should cost less than $100. This was not met because we spent $220 on the arm, but we still managed to stay under the $400 budget given by the class. Another restriction was for the arm to have smooth movement. This was a restriction because the board only has 4 hardware timers, which were already in use by the 4 PWM signals. So my approach was to use software timers in order to achieve the smooth movement required.
The navigation algorithm took input from the LiDAR sensor at startup to create a map of the local area, which includes obstacles, free space, and potential targets. This map is centered around the origin, which is also always the rover starting position. Once this map is created, the potential targets are identified, flagged, and sorted by distance. A target is taken from the front of the list, and a path is calculated to that target using Dijkstra's algorithm. Dijkstra's algorithm is a best first search algorithm that iterates through each point on the map until one of the points it is looking at is the target. Dijkstra's algorithm outputs a path and polar coordinates, which are then sent to the rover via MQTT. Once there are no polar coordinates left in the path, then the PixieCam ultrasonic sensor start outputting information about color and size of the object to confirm if it is a target or an obstacle. Once the object is either picked up by the arm if it is a target or disregarded if it is an obstacle, the next potential target location is taken from the front of the list and the navigation process repeats. One issue with the navigation component is the MQTT functionality. The frequency of messages sent from the LiDAR sensor is so fast that the MQTT callbacks will oftentimes miss messages from the PixieCam or ultrasonic sensor. This hinders target identification, and an effective solution was not found. Here you can see one of the maps created from one of our test cases. The orange is obstacles, which in this case are walls and furniture of the room. The black point is a potential target identified by a LiDAR sensor. These potential targets were identified by calculating the amount of free space around the point, and since there are no other points in this area, it could be a target. In this case, there is only one potential target, which makes sense, since all other orange points have very little, if any, free space around them. If there were other potential targets identified by a LiDAR sensor, then there would be other black points on the map shown here. In ideal conditions, our rover functioned very reliably. The rover followed headings sent by navigation reliably with little error accumulation over time, and the PIXI camera ultrasonic sensors could identify objects reliably. The navigation could identify targets with fair accuracy, and the path calculation was very reliable even with multiple targets. In a few test cases, the rover identified several targets, traveled to them one by one, and correctly identified each as either a target or obstacle until there were no more potential targets to travel to. In harder test cases, the rover would not identify all obstacles in the room. This is due to the limitations of the LiDAR sensor, since objects need to be fairly large to be detected by it. Furthermore, the LiDAR sensor outputs erroneous data points after about 220 scan points, which had to be filtered out or disregarded altogether to get an accurate map of both obstacles and potential targets. Erroneous points were also produced when the LiDAR sensor was operating for more than a minute, and this was only solved by sending a restart signal to the LiDAR sensor during operation. The LiDAR would sometimes send bad health signals after these reset signals, which would put the rover into a fail state, so this practice was avoided for as long as possible. Other sources of error would come from the sensor output being sent over MQTT, bogging down the callbacks. The output from the sensors would occasionally be sent so frequently that the callbacks would be busy servicing the messages, and miss critical messages from other sensors, such as a color signature from PIXI Cam when trying to identify if the current object is a target or an obstacle. MQTT being bogged down ended up being the source of error for other components like the arm. If an ultrasonic sensor message was missed just before grabbing an object, then the arm would miss the object because the distance it was receiving was outdated and no longer usable. To sum up our performance, the rover accomplished the goals we set earlier this semester, and were able to pass most of our test cases. The robustness of the rover was not very high, but this was due to the inaccuracies and limitations of sensors, not so much our algorithms or software design.